Emory. Thank you so much. Thanks for all for coming here on a Sunday morning. So just to kick this off a little bit, let me just tell you a little bit about what I am and where I'm from, what's going on. So I'm one of these people that grew up as a hacker. And so in my teenage years, like my claims to fame are co-inventing format string exploits and coining the term anti-security. And then at some point, I realized that what I was doing had no future. That there was this like moment I remember where I was like sitting in my room and I had like hacked half the internet. It was just like, this can't be right. Like I can't have this much power. I can't wield it, right? I can't be here being able to like burrow in and do things and like things could break. And in fact, I had broken something. And I just remember this realization, just like this, like the only way this can end is badly. And so I quit. I just completely like zoned out of security. I went on an academic track. I did a mathematics. I did a PhD in computer science and became a professor. And I was working on different things, but it always haunted me to have kind of been in this underground and understand how it works and seeing everything failing every day and knowing kind of what was driving that change. And so as a professor, I just thought to myself, if I'm not the one to try to fix it, then who? Like, and if I'm not doing it now that I have a platform, when do I do it? Right? And so I just felt I had this mandate that I needed to take this experience of having been in the underground and try to channel it into making things better in some way. And so I started to have hacking competitions. I started to teach hacking, do all sorts of things like that. I founded some companies. This is actually my third company. And I'm now on leave as a professor at Emory University doing a full-time stint at a company called Keystrike. I want to tell you about. But this is my trajectory. Is that fundamentally, I feel like my calling is I need to make things better when it comes to security using this vantage point that I have, but also using the ability to kind of bring things together and try to ideally simplify. And so the theme today is really about simplicity, and it's driven by a question. To motivate the question, I need to contextualize a little bit. We've been talking a lot about OT here. Like we've been talking about critical infrastructure. A lot of you are critical infrastructure folks, right? And so when we talk to critical infrastructure folks, it's important to recognize where things come from. And so just a statistical test here, like, and it's interesting to hear people's gut feelings depending on their background. What fraction of attacks into the OT do you think originated, or at least was vectored through the IT? Yeah, this is the right crowd for this, right? And so like, so Palo Alto like did a study and they put it at 72%. But like this surprises a lot of people who are solidly not in the cybersecurity domain. Like this is really high. This is the way to break in. And so if we do that, we need to understand a little bit about what we're facing, right? And so what you can do is you can look at your firewalls, you can look at all the things that are being attacked every day, and you can kind of be like, oh, I stop all these attacks over here. This is great. Okay, cool. But that doesn't really tell you anything. What you really need to look at is successful attacks and then work backwards from that so you can learn what went wrong. What are the things that we attempt? Remember, we're fighting an adaptive adversary, right? So what can we learn from impactful attacks? If you take the data together, data is scarce. And actually, some of you are probably privy to better data than I am by virtue of your position and things you probably can't talk about, right? And so with that said, we need some sort of frame of reference of what it means to talk about attacks, right? And so to do that, we always need to kind of simplify into things. So let's think about an attacker who wants to attack a server here. And of course, like as an attacker, as you have probably a lot of you done, you need to do a host of different things. You need to do some reconnaissance, you need to break into the first server, you need to establish a root hold, like get some stuff, then you pivot from that server to the next one. You do all these different things. Like there's a whole bunch of steps that you do in your attack chain to get to whatever that goal is that you're trying to execute, right? So just to simplify it a little bit, let's just take the MITRE matrix, our favorite thing here, right? Like just take the different things that need to happen at the different stages as you're making one step in that attack chain journey. So you establish initial access, you get execution, now you persist on that machine, and so on and so forth. And eventually you move from that box to the next one, right? That's your lateral movement, right? And for each of these, you have so many different strategies. This is like the ever-populated matrix. In fact, this isn't even the full matrix. Everything here has like 9 or 10 different kind of subcomponents, and each of these has like, I don't know how many CVEs. Like this is an enormous quagmire to be following along, right? Like this is like what your sysadmin is facing up against. It's like, hey, I need to be patching. Actually, what do I need to be patching if I look at it? So instead of looking at it like this, let's look at the most common exploits that are being used here, the common attack vectors here. So we can at least see what we're dealing with right here. And so here's something that probably kind of makes sense. Like these are things that you've seen and you've done. And so now we have a template we can use. And with this template, we can start to look at what attackers are doing. So let's just dive right in. Let's look at, I don't know, Sandworm in Russia. This is the GRU, like the state-sponsored military intelligence attacker that attacked a bunch of different things. Like here are some of the things. I'll just put the Ukrainian flag, given that they were responsible for turning off the power and like burrowing into election software, all the different things. That was this team's mandate, right? And like the list is endless in terms of what they do. And if you look at their tactics and techniques that they use, here's what they favor doing. They like using kind of the underground part of Russia to like buy credentials and using those to get into the first hop into the machine, or just doing pretty elaborate phishing. They're the ones who are using some of the more advanced phishing techniques out of Russia, like if you compare them to other groups. And that's like the first step. And so for each of them, they have like their favorite kinds of techniques that they use and love, and actually they have a multitude in all of these different columns for how they move on, right? Have you ever looked at like, can you imagine what these people look like? Just if you had to make a mental picture in your head. A mirror, yeah. So it's exactly this audience, right? Ta-da! So just like here's the wanted poster from the FBI. So I guess one of them is pushing 9 years old. And so like, anyway, this is interesting to kind of have a face on your adversary and know who they are. Anyway, let's move over to China. Volt Typhoon is probably something that everybody here has had to deal with. They have a very different set of tactics that they use, because their mandate was to burrow into critical infrastructure in the West and pre-position digital explosives until it was geopolitically convenient to strike, right? Now, that did get thwarted for the most extent, but there was a long period of time where they were very sneakily going through routers. They were like exploiting like these external routers, things that like were effectively gave them the ability to just live off the lands, like be in the shadows, lurk, move gracefully between machines, and use some of the things that are kind of off the radar what we do. And it's a very different set of tactics than we see, for instance, from the Russian military intelligence, right? If you keep going, and like, for instance, like, I think it was NSA that like found them in one of the telcos, and so like they started pulling on that thread and found that they had burrowed themselves into all the telcos, right? Like as an example of like what they were trying to do. And so a lot of our resiliency is based on the fact that attacks are independent, but the big change here is that suddenly you have adversaries that are effectively gearing up for a large correlated attack against our infrastructure. And that is something that a lot of our risk calculus doesn't really account for. Like you can't do insurance like that. Like it's something that we really need to be talking about a lot more. Anyway, that's Volt Typhoon. If we move over to North Korea, which is more financially motivated, this is like, these are groups that belong effectively to the regime or operated by the regime. And so they are self-financing. You pick out kids from like, from grammar school and you make them, like if they show any province in mathematics, and you kind of train them up to be hackers. And now they go in there and they like just kind of find any means of siphoning funds through ransomware or through like stealing crypto or whatever it might be. So there's a bunch of different groups, and here's one of them. And they favor automation. They really like having their exploits be kind of like fairly new. Like it's usually not O days, but something that can mechanize and automate and create a worm out of it effectively, and just kind of do something that always works. It's a formidable thing, but it's a very different kind of approach than some of our other adversaries here. Moving back to Russia and to the ransomware gangs, it's actually interesting to compare how the ransomware gangs are different than the state-sponsored attackers. They have very different techniques. They have older exploits. Something you don't notice as much in like Medusa, which is one of the gangs that attacked like NASCAR, Toyota, and others, is that they don't really use a lot of O days in the same extent as like the military intelligence. Whereas like the military intelligence, when they need to use an O-day attack, like you see a delay in when they are attacking. There's some permission process of like, can we burn this exploit right now to go this? Okay, right? But here, like these ones try to use things that are just unpatched and kind of move along, right? And then like Iran entered the picture. Like they've poured $1 billion into their Cyber Command over the past decades. They have a very large educated engineering workforce that they've summoned to like 3 different parts of Iran to attack the West, and they're the most destructive outright of these different players. Like they just go in and they want to see it burn, right? But they use very primitive techniques relative to the other APTs here. Like they just use valid accounts. Like if there's a PLC that's on the internet, the Iranians are the ones that will go in first, right? Anyway, so they've hacked a whole bunch of things. Famously, Aramco had to I think they had to take a large, I think there's like a large military helicopter that to bring in new computers after they got completely wiped by the Iranian attacks. There's all sorts of skirmishes that have been going on that are not directed directly at the US, but have also had the US in the periphery here. And this is, of course, escalated after the recent tensions that have been brewing. Anyway, why am I showing you all of this? I'm showing you this because when we start to look at it, not just like this individual APTs, but together, maybe we can notice some patterns. So if we take all these different groups and we just kind of look at how they're attacking, like in this little template that we have here, we start to see some commonalities, right? And so if you look at these commonalities, maybe there's something here that we can use as defenders to exploit, right? And there's something that really screams out here, which is that by the time they're moving laterally, which is an essential step for any realistic attack, they're all exploiting our remote services to move along, right? It's very interesting how all these groups converge on that. And it might be that it's just a fluke. It's just these groups that I picked that all do that. No, actually, it is not. If you look at the data from Palo Alto, I don't know why it's black and white now, but if you look at the Palo Alto data, 86% of lateral movement happens through exploiting these remote services. These are like the remote desktop, SSH, things like that, right? That are open up. So in other words, once the attacker has gotten in, we kind of let them move around. We don't really have layered defense when it comes to defending against lateral movement. It's a notoriously hard problem, but because it's so high, 86%, we cross-checked other data. We looked at MITRE, which puts it at 81%, Mandiant, 83%. Sophos, just looking at RDP itself, is 84%. Like, this is a staggering figure. And it's something that I haven't seen put together before. And I think it's really interesting to talk about that. Why is it interesting? Well, it's because ostensibly it's something that we feel should be protected by the things that we keep recommending. Like, for instance, network segmentation, or maybe EDR, endpoint detection, like the new AIDS antivirus that had to reinvent itself because of tainted trademarks. And so now we have endpoint detection response. And it's on this left-hand side of this attack. It's trying to like prevent that first kind of land here. Multi-factor authentication is a nice complement because it talks about identity and is that covers some of these regions. And then privileged access management ostensibly covers a lot of these, or at least helps address some of these other challenges, and supposedly does something about remote services. But let's dig into that a little bit better. Let's look at lateral movement itself in a little bit better light here, because it's a really interesting part of an attack chain. By definition, if you're moving laterally, you're already inside the network. And that changes so many of our assumptions, right? So if you think about it, here's an attacker, and there's a server they want to get into, and let's say there's a workstation. There's something intermediary, some intermediary they're going through to get to where they need to go, right? And so because they're already in, it means that they're past this endpoint detection and response and some of these like initial controls that we have that are effectively what we call perimeter controls here. But there is something that still protects the rest of our network, and those are the identity controls, the things that we've layered on top, like in places that have these layered defense, like multi-factor authentication, privileged access management, and some others. And so if you think about what the attacker has to go through, these are the defenses that we most commonly see and use, right? And if they are moving laterally, it means that they've already made it here onto the workstation. What I want to argue is that we've made some fundamental assumptions about our identity controls in terms of the root of trust that I think we really need to rethink. And it goes as follows. Imagine you're an attacker right now, and you've attacked this workstation. It's a workstation that's used by someone, right? Somebody who maybe has, maybe it's a sysadmin, right? And so when they use that machine, they log into the network in the morning, Control-Delete, they get a Kerberos ticket from the Active Directory, and it's stored on the device, right? And then maybe there's single sign-on. And so they enter the username and their password, and now they get a SAML assertion and it's stored on the device, right? Maybe as part of that ritual, they went and did multi-factor, and so you feel really safe because there's a second device here, and you hit push or whatever it is, and like, oh, defeated the adversary. But as soon as you hit push, you now get a persistent cookie that's stored on your device, and it's valid for, I don't know, 8 hours, 24 hours, 3 months, whatever it's configured as, right? And that second factor ceases to do anything. You have now reduced it down into a ticket that's stored on the device, right? It's a cookie. Same thing for PAM. You open up a session, and you do the authentication dance and so forth, and now you're opening up a session to something in memory, and it's delineated by some JAW token or something that's in your browser on your device. And same thing for encryption keys. You may have a HashiCorp vault and so forth. And that's also a session. So to be able to interact with it, you also need to have some bearer token, and that token is stored on your device. So all these tickets and tokens and cookies, they are stored on the device that was just compromised. So what we've noticed is that attackers today, they just wait. They just wait until it's opportune. This is the living off the land philosophy for the attacker. They just wait until you authenticate, until they can get your tickets, until you can get their tokens and cookies. They just extract it from your cookie disk and so forth. And then they just use those as you to get into that server they want to do. And there is no anomaly here to pick out. Somebody here wanted to authenticate, right? Somebody successfully authenticated. It's just that there was this digital tailgating going on by an attacker who has access to the device. Like this is something that cuts across all of IT. I've never had pushback against it in any conversation with any company, and I'm talking about hundreds, right? This is just something that we have to live with. That we designed our authentication systems to reduce all of its complexity and glory and power into a token that can just kind of be used from whoever has access to this device, right? So in other words, I actually, I have to have this animation here, slow-mo. Hold on, one more time. And spent a lot of time on that one. Anyway, we don't really have anything here against the remote services, do we, right? And that's such a pity, because if you look at it like a funnel, right? Just look at the opportunity that's here. Lateral movement here, it's the choke point for an attacker. We've over-indexed here on trying to prevent the land part of an attack, right? Having that kind of this outer membrane around our organization, this perimeter. But what is a perimeter today when you have clouds, when you have people working from home? What is a perimeter today, right? We're over-indexed on trying to maintain some sort of a boundary here, and we haven't spent the commensurate amount of attention on the expand part here. But that's where the attacker is constrained. There aren't that many strategies available to move laterally. Why aren't we focusing on blocking that choke point, right? That's the opportunity. It's a critical path for the attacker, right? So just to kind of summarize, we have few techniques available. There's a choke point right here. It's the last step in that attack chain. So if you think about security, rather than thinking about it kind of outside in, why don't we just figure out what the critical assets are and then work outwards from those assets? And that's actually echoing what a lot of our conversations at this conference have been about. Identify what really matters and then try to make those things safer and then work outwards from that. That is something that's missing in the IT philosophy altogether, right? Where is our defense in depth here? We don't really have any defenses that deal with this critical choke point here. This is a discrepancy that I just can't accept, right? And so it boils down to a question, which is a hard question. And it is about, suppose that your machine is compromised and somebody is being you. How could you detect that this is going? What's different between you and an attacker? And just to draw that up, it could be something like credential theft. Somebody just happens to have your credentials, oh, this is me, and just goes into a machine. This happens all the time. This is 45% off, included in, I think, 45% of attacks that we see across all of the Palo Alto and all these different reports here. So credential theft is huge, right? But that's also where multi-factor stuff can help us. But what we're noticing more and more are things like session hijacking. There could be an adversary in the middle, or it could simply be that you happen to put in some info stealer malware, or you just got it off of some bazaar on the internet and so forth, then you now have a token, and that token is good enough to get into whatever that server is. Maybe it's a SaaS service, and it just accepts your things blindly, right? Or And this is the most nefarious. Your machine is a proxy for the attacker. And now, what is the difference between the traffic coming from the attacker and you? So this is an interesting question. How can we detect impersonators in these circumstances? And so let's hear it. Let's hear some ideas. What can we do? MFA. So if you do MFA, and so here, MFA is going to do a lot for you, right? This is the purpose of why MFA proliferated. Like, this is why it proliferated in like 2009, 2010. It's because of credential theft, right? But for the other ones here, if you've done MFA, then that's just the persistent cookie you just steal off of here, right? Or if you're an adversary in the middle, maybe you're doing a push and you don't realizing you're doing a push on somebody who is an intermediary, right? And same thing for workstations or proxy. Like, you just wait for the person to authenticate and then you flow along. Even if it's a YubiKey or whatever it might be, it's all the same, right? It's just a point in time, and like the adversary is privy to it, right? Other ideas? Yes. But like, but like the person on the workstation has access to the server. Like, you're supposed to be able to have access to the server. Let's imagine like a sysadmin, right?
Yeah, but there's some behavior that's expected that expect that
Okay. So you want to do some sort of behavioral analysis of what's happening on that server or from that server, right? Okay, so like a machine learning type of approach, okay? More ideas? Yeah. Ah, okay. So like a positive control, like figuring out what's good, not just what's bad, right? Interesting. More? So those are great. Like, here are some examples of like how this can be tackled, right? One of them is just, let's just keep asking the person if they're still they, right? This is the banking approach to the problem. Actually, there's many different places that are just like, oh, you're doing something now that's slightly more risky. Let me check again. Like, are you still you? Just like push that button. Like if you see a Google employee, they have like a little YubiKey Nano, and they just like keep tapping it. Like, it's like a dance. Like, there's a word. Okay, I have to like authenticate every command. It's so automatic that they don't even notice it, right? So that's step-up authentication. And so like you need more identity. Machine learning, like for instance, you could detect that there's something anomalous about the authentication itself. Maybe it's coming from a long chain. There's all sorts of things you could look at in the authentication graph and so forth. Maybe some anomalies relative to baseline, you were saying. Or here's a different one, which is to profile something about the employee, like maybe how you type or how you move your mouse, and just to try to see deviations from that kind of baseline. But if we think those through a little bit, let's think about step-up authentication, right? Find me somebody who likes multi-factor authentication, right? Like, find me some love for that, right? It's done a lot, but people hate it, right? And what happens when people don't like our security controls? They work around it, right? And then they also alienate us as security professionals from doing anything useful because they hate us, right? Like, we don't want to alienate our people. So like security and convenience is a real trade-off that we need to think about here. Also, like, what does it mean to be more risky? Now you have to encode into your system what constitutes risk. So you have to say like, that thing here, that's more risk, but not that one, right? So like in the banking applications, you have like tons of if statements that are like, this is a wire transfer here, so that's bad. And like, that thing over there, that's not bad. Like, it's like elaborate logic that you have to put in all the layers of the application. Of course you leave things out. Of course things change. So do you then just default to always ask, right? Like, how often do you need to authenticate to do one thing in a banking app today, right? It doesn't actually solve the problem either, right? Because you're doing the same authentication in a point of time and you get a token. And so if somebody's on your device, so this is great against credential theft, but all the other ones, the attacker just waits, right? Or blends in when you're tapping your YubiKey Nano and just like, oh yeah, I also want to like steal all the files. Tap, great, thanks, right? Machine learning. So like there have been interesting works here about like login chains and behavior and so forth. And that of course assumes that you have enough data so that you can distinguish attacker traffic from something else, right? But we're talking about an adversary that's living off the land. Like, by definition, they're trying to blend in. So that's a very strong assumption to make here. Also, like, if you are stealing cookies, you're not authenticating. You're just riding along with somebody previously authenticated, right? And the same thing here for biometrics. Like, you will have a personalized model of Keystrike timings. That's great, like being able to understand that this is the person and so forth. the error rates that we get out of it is between like 1 and 5% if you look at equal error rate, like false positives equals false negatives and so forth. That's less rosy than you think. There's a lot of interperson variability in how you type and so forth. And like, what happens when you break your arm, right? Like, are you just locked out? Like, there are like cases that just make this implausible to really deploy it right here. And actually, there's a more fundamental thing here, which is this idea of trying always to model reality. Like, and this is so pervasive now in academia and in various places. Just like, oh, we have an AI hammer, we must use it. Right? Just everything is AI, right? If you think about where AI is strong, it's where like you have a baseline where you can effectively have the like law of large numbers at play here. Like there's enough like good stuff, and then there's like anomalies, so you can clearly delineate that something is different. That doesn't work when you're trying to deal with extreme cases like an adaptive adversary, right? By definition, you don't have data about O-days. You don't know, like you have unknown unknowns that are in here. How do you actually have a powerful and expressive enough model in whatever you came up with in your machine learning latest monster of the week to be able to adapt to a changing reality when like the ground is changing under you? That is a hard problem. That is not something that our tools in machine learning are built for. There are some research into things that are more into this kind of extreme value theory rather than just kind of average kind of statistical behavior, but we're not applying that. We're not using it, and we haven't seen any successes with it really, right? So this whole approach has issues. So what I wanted to show you is a different take on all of this. Let's try to just flip the page here and just kind of let's think about this question again. How can we detect that someone's impersonating something? And there was a great idea here, which is, what does a normal person do? What's different about a normal person using a computer and an attacker who's exploiting that computer towards something? Okay? So here's your workstation. Here's your authorized person. You might enter something into that machine. You now have a session, an authorized session into some server. Let's say it's a jump box here. And the problem is that you have an attacker who also has access to your workstation. They may have a malware, an implant, or just direct connection, whatever it might be. And during your session, they can even inject something into it, right? Or they can spawn another channel in the background. There's something that like happens during your session. There's no anomaly to pick up. That's the issue here. And then you notice that the attacker is making commands remotely, right? Like they're remote button. We're assuming they're not like physically on the device and so on. Whereas the authorized person, they're making these commands with their keyboard, with their mouse. So there's no difference here in the output when it comes to things from the machine. It's really indistinguishable, but there is a difference in the input. Maybe that is something we can use to delineate. What if this server here on the right-hand side, or like, let's say that you have an agent on both sides here, and the first one just says, "Hey, I noticed there's a command here that's being entered. Was it physically entered on this machine, like keystroke by keystroke?" And correspondingly, you have an agent here that says like, "Oh, I see there's some command being entered here, where it's an API call, or if it's a keystroke in an RDP session or SSH or something like that. I'm going to withhold that keystroke until I get proof that it was physically typed on that authorized machine." So now suddenly you have a scenario where the authorized person, they can just kind of type away. By typing, they're proving that they wanted something to happen. Whereas an attacker, even tries to inject a single keystroke into a session, gets caught. It gets blocked because there isn't that proof that they physically made that character, physically wanted an API call. That's a different idea about it. And what I like most about it is that it's simple. And I feel like we need that in security. We need that actually across all of computer science, is that if you think about the constructs that you use, if you think about the programming languages you admire, the papers you love, right? They're all simple, aren't they? Why aren't we seeking simple solutions for hard problems? Why not? Why is it automatic that we always need more complexity to deal with current complexity? If you invest enough time into tackling a problem and you think past the initial solution and you find some unifying thing, you distill the core of a problem, then you found something that is a pliable construct that can be reused. It's the nugget that can lift others, right? So like you found something that is the foundation. And that I think is the interesting part here, right? So in this case here, like because it's simple, it actually has a lot of properties that are really nice. For instance, if you by typing you're proving that you're you, there's no friction for the end user. They don't have to do anything special. They don't have to reach for their phone to hit accept or something like that. They're just proving their presence by being present, right? There's no false positives here because if you think about it, I get a keystroke into my server and I'm either going to get a proof that somebody physically typed it or I'm not. If I get the proof, we know it's good, right? Like something like somebody physically made that keystroke. And if we don't get the proof, there is only one possibility. It's an attack. You've removed the whole kind of inference about like the model of is this possibly good or bad. You've completely annihilated that thinking by simply attesting good behavior systematically, right? The same thing here, like if you think about overhead, like what do you need to do to make this happen? There's no overhead in terms of deployment. It's a little agent. There's no overhead here in terms of like how much CPU you're taking. You don't have to make any big models or inferences. You don't need a GPU or anything. You're just saying, hey, I see that the Bluetooth stack or the USB stack made a keystroke, and I am here borrowed as deep as I can into the operating system to be able to certify that. Hey, I'm going to make a signature. That's it. Right? You can make it very easy like that. So that's what really like. This is why I like this idea, and it also allows you then to do things like block. Somehow we got fed this idea that really our goal with all of our security controls is to create signals that we then pour into this giant SIM, and that SIM then gets poured in front of this giant SOC team that's like ripping their hair out, and they're trying to look at it and like figure out the context. They're like, okay, so there's a login from here, and this is going on. It's from Poland. Like, what's going on? Like, and they have to make a call if this is good or not, right? Somehow we like outsourced all of these things to just finding signals instead of trying to prevent the problem in the first place, right? Trying to stop an attacker as they're moving. Like, when did that stop? Right? Here we can identify, you can actually block the connection because like the keystroke doesn't go through. You know that something is going on, and that means you can remediate. You can do something about it, right? You can like lock down that machine, or at least require something more going on right now, not tomorrow when the SOC team gets to the alert, right? If they get to the alert. And that means you can start to orchestrate some of these other controls that you have. You can like turn off the account, or you can tell the NAC to isolate it, or you can, like whatever you want to do that you would want to do if you had a strong enough signal to do stuff, right? So, and then like this isn't just like interactive sessions. You can do the same thing for like all the SaaS services, API calls, like sending an email. Why should somebody be able to send an email if they didn't physically make that happen on their machine, right? Like a business account taker is a real thing. Or send a message on Slack, like Okta got hacked this way, MGM got hacked that way, or commit code into GitHub, or like open up a new virtual machine or shut one down on Amazon. Like, why should any of these actions be possible if there wasn't that physical intent behind it, right? Or same thing like for file sharing, or any, like in fact, everybody in an organization has access to some critical data. Like everybody has some sort of privileged access, and you really don't want any of that privileged access to leak over to an adversary who gets access to their machine. So we should be certifying things end to end. Like this is what zero trust thinking is supposed to be all about, is to find that way of making sure that only this person can do this, right? So anyway, like this is an idea that we had in our lab at Emory, and so I took a break and made a company around it. We have, I think, 10 million in funding, 22 employees, 2 patents. Our product's being used in like 35 different countries. So it's actually really fun. I was thinking that, like, let me look at the timing here. Do you want to just see it? Do you want, like, I can just, yeah, okay. Here, I'll just show it to you here. Okay, so what I have here is my machine has been actually hacked. And it's been hacked by one of you. So who wants to be my hacker? I need a volunteer. Yeah, I mean, so there's a waiver. No. Okay, we got a hacker in the back. Great. Okay, so you actually now have remote access to my computer. Actually, let me pull up some fun stuff here. I'm going to pull up like a little PowerShell here just to kind of have it around. And I also happen to have remote access to This is a I don't know, sensitive system. Oh, it's actually it's this electrical. It's a SCADA controller. Oof, for an electrical. You really don't want to have access to that stuff, right? So anyway, I'm being taken over. Look at my hands, right? So try typing something into this PowerShell that's right here, right? Okay, so I'm being hacked here fully, and of course, like I mean, it's a demo, so like it's interactive. This of course happens in the background when you have a real attacker. But here's an attacker, and actually, like I did this at one point, and the first commands that the person entered were format C and shutdown. And I was like, oh. So please refrain. Anyway, so this is stuff that's local to my machine, right? But now you see that like notepad that's there in the remote desktop over there. Try typing something into that notepad here. So you can like type some text or actually maybe like close the notepad or actually try shutting off the power grid. It's connected to the Spanish power grid. It'll be fine. So nothing is coming through because I'm not typing. I'm not physically making those keystrokes over. There's no attestation. In fact, they're being blocked, but they're also generating alerts because there's no proof that this is going on here. Yeah, so I mean, so you notice that you can hover over things, right? Try hovering over like the X or the start or so forth, but you can't make an actual click, right? And so this is like the Windows version we have for Linux and other things like that. Now you're running something local on my machine. Yeah. You want to keep going? Anybody else want to try this? Like it's interesting, right? So, but like if I go here, like so, if you give me a sentence here, like, hello, like I can just type and I can turn to the power grid in Spain again. And I didn't have to do anything special. I didn't have to reach for my phone and accept. Just by typing physically, I'm proving my intent. Like that's how simple we can make things. Why aren't we doing that, right? So anyway, this is a kind of any questions around this demo or not? Yes, go ahead. Um, Right. Okay. I mean, that's a great question. Actually, let me repeat here. So, the question is like, why can't you just synthesize keystrokes effectively as an attacker? So, the assumption in the software version here is that our agent still has greater privileges than the attacker. So, the gambit is you now have to invest in an ODay to do privilege escalation to get kind of kernel level access to that machine. Now you have to write a keyboard driver, and that's the one where you start to input things here. And that's expensive, right? And actually risky because that's where EDR and stuff is strong, is to find those kind of, like everything lights up like a Christmas tree when you're doing a privilege escalation, right? And so for those that are just lurking in the background, they're living off the land, they're maintaining user level access and just flowing along with that, they can't actually synthesize USB level or Bluetooth level keystrokes, certified. So in that sense, that vector is out. Now, I mentioned this is the software version. We have a skunkworks version of a hardware version of this thing here, where you just plug your keyboard into a little dongle and then into the computer, and the certification happens before it even reaches the computer. So even if NSA burrows all the way down to the firmware or wherever levels, right, they can't create new attestations. There's no attack surface for it to latch onto. Like the keystroke has already been certified by the time it reaches here. So in terms of integrity, there's no harm. So for like our high security clients, that's what we're building. Yeah. So the idea is that the machine you're using, where you're entering your keystrokes, that's where you have that agent. It doesn't matter how many hops you go through, even if you go through one at work. You could have an agent there too, but you certify that like this is my machine, it's been set up, it's there, and that keystroke physically came from you. Now, if it's like bring your own device, then like I mean, you have some other problems in your organization. But yeah, yeah. I mean, so that and like we have a limpy version of like a contractor version where you can go through the web, but like now you're certifying it just from like browser root of trust rather than something bigger. But like that's to work around that case. There's a question. Really good question. Yeah. So right now, like an on-screen keyboard is not going to work, right? It's because it's a virtual thing. But there are variations of on-screen things that are kind of like lower in the stack, and so they would synthesize an actual keystroke, and the driver would be recognized as human input device, in which case it would work. But yeah, that's a legit question, and like we don't have a good answer to it. Yep.
Model, like it's okay,
Because it's simple. SDX is not simple, right? Like it's actually very complicated. There's a lot of layers to it, right? And there's a lot of side channels and things to explain and so forth. What we're doing is like literally we take a keystroke and we make a signature around it. Like you need very small microprocessors to do that. And that's it. And so like there doesn't even need to be a full USB implementation. You get around with very little when you're just kind of almost transparent in the middle. That's the gambit. Mhm. So for the software version, oh, you mean like for the hardware, or for the hardware? Yeah. So okay, so look at the hardware version. You've burrowed in, you have a kernel module, and so forth, right? By the time your keystroke appears in the system, the signature, like the private key, is on this little dongle. It's already been signed, like that this keystroke came at this moment from this device and this user, and that just arrives through like the regular kind of USB interface, right? So you get that. I mean, you can withhold it, but you can't really modify it because you can't recreate that key, right? You'd have to get at that private key to be able to make the signatures. So that's what I guess. More questions? Yeah. Yes. I mean, in theory, it works everywhere. Like you even work on a Chromebook. Like we've implemented it for Windows, Mac, Linux. On the client side, on the server side, it's Windows and Linux, like SSH. No Tableau OS yet. Okay, I'll put it on the backlog. Okay. You had a second question, yeah? I mean, so like you're trying to protect that server, right? And so it's really a question of like mediating the access to the server. And so like, could you lock a legitimate person out? Like if they don't have the agent installed, or I don't know, the world is on fire and like everything is down. Like we're used in critical infrastructure, we're used in power plants and like the biggest water utility in Arizona and so forth. Like so we built in those kind of like get out of jail free cards. Like there's a way to get around, like effectively it's like an offline kind of key that will just get you around the product if need be, because you need that for first of all for compliance, but also just for safety, right? You had a question? Uh-huh. Yeah, I mean it's a great question, and so there's like kind of two answers to it. And one of them is that in many settings, that script is either something that's under source control and like it has to have some sort of like with good practices you want to have in a GitHub and put in, and so we can mediate that access and make sure that you were the one who committed that script into the repo and kind of bootstrap trust that way. Second thing is that if you're running it off of your like regular workstation, just like a script like that, you have a lot more apertures into your system than you really want to, right? Like it means that you have not just RDP, you have PSExec or WMI or some other protocols that are open, and that counters the whole segmentation thing. Like you really like think about it more like your jump boxes, the things that segment your network. That's where you want to have a small aperture, and this reinforces that bridge, right? Make sure that only this flows through. So in that sense, like in that other segment, that's when you have a machine that has your SSH scripts and other things like that, right? Now we can, of course, have special accounts that are brought aside, for instance, for contractors or for scripts, and that's supported by what we have here. But I would recommend against. You had another question.
Yeah. So before I say things that are going to sound questionable, I just want to say, like,
Uh-huh. Mhm. Yeah. Yep. Mhm. Mhm.
how much are we buying concerning
Right. And I wish I had like data to back it up, but like the ballpark, like at least for now, you need somebody who is able to get like privilege escalation on a machine, write a kernel driver that simulates an HID device, and at the right moments writes the keystrokes into a session and so forth to be able to piggyback it. So like a session in the background, like you're not gonna.
okay, so it's
Right.
like
It is, yeah,
okay.
and especially at the very, very beginning where they have to do all the research and so forth. Yeah, but it does. It makes it really painful because now the timing aperture for you to do stuff is very limited, right? Like this channel of using RDP and things like that kind of closes. Now you have to like search for an O day or something in the protocol, right? Yeah. Yeah. Yes. Uh-huh. Yeah.
But like it seems like it's gonna bother time, which is really important.
Right. But it does something a little bit more fundamental, which is that it connects the intent, like the physical intent of someone, with where that intent is supposed to do,
No,
independent of the technical stack that it's going through. That's the whole idea of like zero trust at like a device level, is to bypass all the things you have to trust in the middle, right? And so in that sense, like it does do something very fundamental on that route. Yeah. 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 Right. Uh-huh. Okay. That's fair. That's good. There's a question there in the back and then here. Yeah. Uh-huh. Yep. Remember, if you shut this down, like if you turn it off, you can't get into anything because you need to certify every keystroke, right? So you do need to write something that injects a proper keystroke, or at least takes over the process that we have like in kernel level to make those signatures. You have to do a lot of work to certify that you're allowed to go into the remote host. Now the workstation is toast. It's already toast. Like you can do your privilege escalation and so forth. But to get from that one laterally to the next one, you need to do quite a bit of homework. Yeah. Or you need to find an ODay that works remotely against that machine, and then you're back in business, right? But that's expensive. And that's the whole point of security, is to make it expensive for the attacker, right?
It sounds really but
Huh?
it does sound like really the easiest way to break it is to get the credit. And
Huh?
if you can't get the credit, you get served by the user.
Right.
So as long as you have fake credit, it's it'd be harder to
Right. I mean, so then like it's about like, I mean, it's stored at TPM, but mediating the access to TPM, you need like kernel level things. Or if it's the hardware version, you need to know get at the private key, you need to solder, then that's where you're expert, right? So like, is it unbreakable? No. But that the latter requires physical access, which like cuts off a lot of the attack surface, right? Right. Yeah. So in that sense, like it does make it significantly harder in the sense of like this idea came about thinking about what would be the worst nightmare for an attacker. And like I just thought back to my own experience. It's like it's getting into some box somewhere and not being able to move from there. Right? That you've already committed a lot of things to get there. You've already maybe wasted some of your research, but you can't get to your target. Like that's really stuff. Yeah.
So I mean, yeah, I think we get how the technology works. That makes sense. Really, the whole point that is pushing the flare of the attacker can have shoot up a flare by pushing that workstation fully to making all the kernel stuff. So this really works well that like
Yes. I mean, it relies on EDR being there to protect it. Yeah. Right. Yeah. Another way to think about this, if this had come out like 10, 15 years ago, I don't think we would have MFA the way we do MFA today, right? We're relying on MFA as a crutch for a lot of different things. What if your keyboard was your second factor, right? Like we dislodged the whole authentication from like who owns this session, who wants this command to be executed, right? And same thing with privileged access management. The whole point is only this administrator can run a command on that server. Like we go through so many hoops to try to make that, and we still can't do it. There's a lot of things that are claimed to be PAM, but really aren't if you dig under it. And suddenly, like if you do it at this level, you have that kind of a primitive that you can use. Like only this person can do that, right? That's very powerful. So like there's a lot of things where it kind of fit in. So I appreciate that. I think there was a question there. Yes. Yeah. I mean, it's currently a prototype, so like it's not baked into the prototype. But like that's the question. It's like, so we're talking with some vendors and so forth that have the like tamper-proof things, and so the question is, how expensive do we want to make it versus how secure it needs to be? And so the question is then also about the viability of the different threat vectors, right? If it is that you're doing physical protection, then like that's a very different stack than like the kind of remote protection. You could, like, there's no reason you couldn't make it tamper-proof and like just gonna destroy the device by opening it, or like make it reliant on like how it's like soldered together. And there's lots of things you can do, right? But like sky's the limit in terms of how much you invest in that. Was there some other question I missed here? Just to kind of draw this to a close. So just like what we talked about are these identity controls and like how they fail when you have an attacker who already has persistence on your machine, right? Like we talked about the different APT groups and what they do and so forth. And in particular, we noticed that lateral movement is this choke point that we haven't really been talking about, and like we're not exploiting as defenders to try to stymie an attack. Now, of course, it's very late in the attack by the time they're moving laterally, but that's the reality of where we are when it comes to IT security. Like we don't have better defenses than that. Like our membrane is so porous that it's on sale for a few dollars on a bazaar. Like, oh, you want remote access to like that workstation and that workstation? You can just buy it. And like it's a separate group that does it. That's why there's a delay between like the initial access, like from the InfoSealer malware and like the ransomware group buying that access and then taking it over. Like there's an ecosystem around this. This is so common. But like, what if we could plug this? Suddenly you can strike. You can do it really simply by just ensuring that every command has physical input, right? It's like a really easy idea. So that's just kind of drawing to a close what we talked about today. Thank you for all the questions. We'll be here at like the Keystrike booth over here if you want to see more demo or anything around it. And happy to just have a conversation here. Thank you very much.